So now that you've seen the magic triangle, you can solve for current really easy. You just cover up the I, and you find out that it's power divided by voltage. So 1600 divided by 110, and so on and so on. And each one takes a certain amount of current. If all of them together take more than 15 amps, you can't run them all together. Well, we know that that's going to be the case once we start out with the hairdryer, because it's 14.5 amps. And so here we go, all of these. So which ones can you use all at the same time? If you want a total of 15 amps, well, you can only use the hairdryer by itself. You can only use the dishwasher by itself, but you could use the microwave, the toaster, the coffee maker, and the flat iron all together. Now here's the truth to electrical circuits. A dishwasher needs its own circuit, as does a microwave needs its own circuit. So you're never going to have a situation like this, to be perfectly honest with you. And that's just electrical code. So if anyone has any interest in electrical code, boom, there it is. So let's have you do this. You have this one is horsepower, so you have to actually convert this to watts. Remember that conversion I gave you? 745.7 watts is 1 horsepower. So you can tell how many watts this is right away. So pause this and calculate really quick. You could do 6 really quick calculations with the calculator, write them down, how much current each one of these 6 items is, and then see which things you can use simultaneously and which things you might want to have on their own circuit to do that. You also note that this one is 220 volts and this is 220 volts also. So we'll talk about that in a second. Pause this and see what you get. So what you probably found is that you can't run most of these together with each other. There's a lot of them that need their own. The computers doesn't take a whole lot of power, a whole lot of current. The lights aren't going to take a whole lot of current. In fact, a 400 watt light would be crazy huge wattage. You're not going to see a light, but that would be maybe a total of all the lights, not each of them. A laser engraver takes a lot, 3D printer takes a lot, but the truth is anytime you have a 220 volt circuit, those have to be on their own circuit altogether. So these would be separate circuits altogether. You can see the bandsaw takes 7-ish watts. You probably could run A, B, D, and E close together, or on the same circuit. I don't have the numbers in front of me. You can check that. But the laser engraver and the 3D printer would have to be on their own just because they are 220. So let's take a look at torque. Torque is the twisting force on a shaft, and it's found by this formula tau, which is a Greek letter. It rhymes with now. Anyway, it's for torque. It's distance times force times sine of theta, or force times distance, same as the work actually, but you multiply it by sine of theta, by the angle that you apply it. So when the angle is 90 degrees, sine of 90 is actually 1. So you're multiplying it by 1. Torque is just force times distance if you're applying a force at 90 degrees to the angle. So if this is a wrench and I'm pulling down like this, as long as I'm pulling perpendicular to the bar, straight down, then I have maximum torque. But as soon as I start doing weird things, like if I am trying to go down with this to pivot it down, but I apply a force maybe this way, then I actually lose torque. I have a sine of an angle that's not 90. And so that actually changes things a little bit. So let's do a practice. 100 pounds of force is being applied at the end of a lever 3 feet long. The force is applied at 90 degrees. So what's the torque produced? 90 degrees makes it easy. So you just have, here's our picture. We have what we know. We have a force of 100 pounds and the distance is 3 feet. So torque is force times distance. 100 times 3 ends up being 300 foot-pounds. So again, force times distance, the radius is 3 feet, the force is 100 pounds, 100 times 3 is 300. And since it's 90 degrees, sine of 90 is 1, so it just kind of goes away. Moving on, we have power calculations. So this should be the last equation that you have. It's torque times RPM divided by this constant of 5252. So using the previous problem, how much power will be generated if the force applied if the force is applied at a rate of 200 RPM? So if you're applying that downward force at 200 revolutions per minute, so you're applying that force and you're causing that thing to spin. So we take, oh, that's supposed to be the tau sign right there. Tau, or torque, times RPM divided by 5252. Well, in the previous problem it was 300 times 200 RPM divided by 5252, divided by, is 11.42 horsepower. So that's how you calculate rotational power or torque power. All right, your turn. A shaft is a force of 13.5 pounds, applied 2 feet from the pivot. What's the resulting torque? And we're going to say that it's applied perpendicular at 90 degrees. And then the second part is how much power is generated if the torque produced at 3,200 RPM. So please pause this and work this problem out. So you should have come up with, again, that's supposed to be a little t there for torque, force times distance. Force is 13.5. The radius of the distance is 2, so you get 27 foot-pounds of torque. And then power, I don't know why all these x's are here, should be little torque symbols. Equation for power is torque times RPM divided by 5252, so we substitute 27 for torque there. It's at 3,200 RPM was the given for us, and we divide that, we get 16.5 horsepower. So let's finish out with fluid power. Fluid power is operated, anything operated by a compressed fluid, and a fluid could be some type of air or gas. It could also be a liquid. All those follow into the category of fluids. They are low load carrying capacity. Some do, I guess, have low load if it's an air, and they require mechanical stops if they're not used as servo motors. So mechanical stop just means something that's just stationary and it stops once it presses against it. So let me give you some information about this. There's two types. There's hydraulic and pneumatic. You may have to Google how to spell those. Hydraulic and pneumatic. Pneumatic is P-N-E-U, pneumatic. Pneumatic is operated by air or compressed gas, usually air. And hydraulic is operated by either water or some other fluid with a very low viscosity. And viscosity means its resistance to movement. A low viscosity means it flows really, really easy. So there actually is specific hydraulic fluid. It's really toxic and gross and stinks and it's nasty, but it works really, really well. We're actually going to build some stuff using hydraulics or pneumatics, and we're going to use water just because it's free and it's clean. So advantages of pneumatic power. It's lightweight. Compressed air is really easy to find. Compressed air is easy. It's everywhere. Disadvantages of pneumatic power. It's not very efficient. It's not very accurate. So when you apply a little pneumatic syringe and you push it in an inch, the other end should go out exactly an inch, but that doesn't happen because air compresses. So since air compresses, then you push one syringe in an inch, the other one won't go out necessarily an inch because the air inside there compressed. So it doesn't really work very well for that, and it's not very stiff. If you're trying to lift something up on pneumatic power and you push a syringe in to do that, it compresses before it starts to lift, so it's not very stiff again. Hydraulic power, it provides an advantage, large amounts of power. It can move high loads at reasonable speeds. It's not very noisy. There's not a generator that's moving or an air compressor that's making noise. It's quite efficient. You push in an inch, it will move out an inch. Liquids do not compress. Disadvantage of hydraulic power, it's more expensive because you have that special fluid, and it requires a energy storage system. You have to have pumps. You have to have reservoirs for that fluid, and it can be susceptible to leakage, and hydraulic fluid is really nasty stuff. You don't want it to leak. Water is really nasty to electronics, like our VEX stuff, so it's dangerous to use that. So we have to be really careful when we use water in hydraulics. So if you're going to calculate fluid pressure, P is for pressure, F is force, and A is area of the base of the fluid container. That's the area of this plunger. And so if we're going to do some fluid calculations, make sure you note this in your equation. I think this is the last one. Force is being applied down onto this, this cylinder there, that plastic cylinder. And A is the area of this circular disc. So the equation for the area of a circle is pi r squared. You'll have to apply that. And so here's your turn. If you have 50 pounds of force being applied down onto a 1-inch pneumatic cylinder, now 1 inch, it always is referring to the diameter, never the radius. So if you have a 1-inch diameter, what's the area of that? Well, you have to find the radius first because it's pi r squared to find the area of that circle. And you'll recall you need to find force and area to find pressure. I've given you the force, you need to find the area. Diameter is 1 inch, find the radius so you can find the area. Please do that. That means pause it. And you should have gotten this equation. We knew that the pressure, the power or force is 50 pounds. The area is pi r squared. Radius is half of that diameter, which is 0.5 inches. So when you plug it into your pi r squared equation, you get 0.785. And 50 pounds divided by that is 63.7 psi. So here's one other practice. It looks a little bit different. Hydraulic has pressure of 150 psi is applied to a piston that's a 4-inch diameter. So you probably need to find radius. And a 9-inch stroke. That means it goes down 9 inches. You know the distance. You know the pressure. You can find the area. What is the power? So remember, go back to your power equations. I believe power was work divided by time. Do you have a time? I believe that you do. Do you know the work? Work is force times distance. Well, you have a distance here. So you already know the distance and the time. You don't have the force, but you can find force using your pressure equation. You have pressure and you have this diameter for area. So you can find that. This is probably the most complicated multi-step problem that you'll have for these this unit. So please pause this, practice this, give this your best shot, and we'll look at the answer. So you start out with 150 psi equals force over area. If you use pi r squared, remember your radius was 2, you get an area of 12.6 square inches. So force is if you solve for force, you get pressure times area. Remember, you can make this a magic triangle, and you get 1,890 pounds. So that's your force. Your distance is 9 inches, so your work is 1,418 foot-pounds. Divided by time of 2.5 seconds is 568 foot-pounds per second. Divided again by 550 foot-pounds per second for 1 horsepower gives you a little bit over a horsepower. So that's it. Now you should work on your practice problems, and let me know if you have any questions.